Good. Okay, so today is October 3rd, 2022, and we are covering chapter 3, 2D motion. Everything that we did so far is just a generic treatment of 2D motion. Okay, we didn't give you any, I didn't give you any specific examples of 2D motion, but there is this specific example of 2D motion that is very important. Extremely important, okay? Is that what we call projectile motion? So let's go, and I need you to see 2D motion displacement. Let's see if I can I can take advantage of this part here. Let's see. Okay, now, okay, here you go. That is projectile motion, okay? Let me get started. I'm gonna copy that. I'm gonna copy that and paste elsewhere. This is a very important problem. And back in the time of Galileo Galilei in the 1500s, they were, people were trying to figure out how to predict the path of a projectile like a cannonball, propelled by a cannon. And that was the first step was to look at those equations that we're looking right now, okay? That of the projectile motion. So here you go. At that time, they quite of knew more or less that it was a parabola, but they couldn't get a real mathematical prediction of how the path of the projectile could be predicted, okay? And now we have this type of problem. Okay, so let's see, here you go. Projectile motion. Projectile motion is section 3.3 of the book. Projectile motion is section 3.3 of the book. Okay, so here you go. What is projectile motion? You have to remember this definition. What is projectile motion? Is motion of a projectile that is subjected only to the acceleration. Is motion, let's see, what's projectile motion? Is motion of an object, here you go, that is subjected only to the acceleration of gravity. Okay, is motion of an object with an acceleration, here you go, with an acceleration equal to the acceleration of gravity. And at this point in time, you should memorize what the acceleration of gravity, okay? So here you go. I'm going to stop sharing momentarily, okay? And this very moment I'm holding this pen here, okay? And this pen is doing some sort of motion like that. This pen, under those conditions, is not considered a projectile, okay? Because its acceleration is not 10 meters per second squared. However, the moment that I propel this pen, either release this pen in one dimension, okay? Either release this pen in one dimension or propel it so it describes a given path in the two-dimensional space. Remember, the moment I release, the moment I lose contact with this pencil becomes a projectile, okay? While it's flying in space and subject to an acceleration of 10 meters per second squared downwards, approximately 10 meters per second squared downwards, it becomes a projectile. That's how you should see. That's the very definition of a projectile, okay? Subjected only to 10 meters per second squared. The acceleration should be subjected on 10 meters per second squared, okay? So how do we illustrate the projectile? Here we go, illustrate the projectile. Like something like that. We have this object at the origin of the X and Y graph. And by definition, this object, I'm not sharing the screen, right? Let me share the screen. Here you go. Okay, here you go. So we have here an illustration of the projectile, right? We have this object at the origin of the X and Y axis. It will be subjected only to the acceleration of gravity. And that's the G vector that you see here. Okay. Which is equal to what? Minus G. G here is always a positive number, 10 meters per second squared, in the Y hat direction. Notice that the vector points in the negative direction of the Y. Okay. So we're going to solve this problem. Given an initial velocity of V0, okay, non-magnitude, what does it mean? Non-magnitude and angle. And knowing that, given that the initial velocity of an object, an initial vectorial velocity of an object, vectorial velocity of an object, V0 is non-magnitude and angle, and that the object is subjected onto the gravitational acceleration. Find the equations of motion of this object, okay? Of this object, which, by the way, is a projectile. Okay? What you have to know, okay? So here you go. The best way to visualize that. Let me see if I can get a better graph here for you. No, I don't. I'll have to do that from scratch, unfortunately. I have this slide somewhere, but it's not here, okay? So what you have to know is the following. Here you go. This object is subjected just to a vertical acceleration. It has a vertical acceleration, uniform acceleration, and no horizontal acceleration whatsoever. Okay? So here you go. So I'm going to write that down here. This according to the statement of the problem, the object is subjected only to a vertical acceleration, no horizontal acceleration whatsoever. Okay? Consequently, its acceleration can be written in terms of, here you go, but he'll write it in a different way. Here you go. Acceleration of the object is equal to, I'm going to put it this way. Acceleration of the object is AX, right? Like every AX in the X hat direction plus AY in the Y hat direction, okay? I'm not going to put G here. Yeah, I'm going to leave this way. Since there is no acceleration along the X direction, I'm writing this component being 0 x hat, right? And since there is only downward acceleration in the y direction, you write that down as being minus g y hat. Okay, and I wrote here, 9.81 meters per second square. Okay, so that's how is the acceleration of this object. So let's revise again. No acceleration along the x direction, but uniform acceleration along the y direction. So what does it mean? What does it mean? Okay. Oh, it means what does it mean? It means that the object will be uniformly accelerated along the vertical direction and will have uniform motion, constant velocity. Okay, uniformly accelerated means constant acceleration. And we have uniform motion along the horizontal direction. That's what it means. Okay. So the situation is going to be like that. Here you go. If you have constant acceleration along the y direction, I'm going to, you know what? I'm going to put, instead of using the number, I'm going to put the letter here. Okay. I prefer to use letters rather than numbers. The letters give a sense that more genetic value. Let's not forget that it's going to be minus g because g is always taken as being positive. G, that's why I'm putting the negative there, greater than 0. Okay. What does it mean? Okay, it means two things. Two things. One, the object will be uniformly accelerated along the vertical direction, and two, the object will have uniform motion along the horizontal direction. And so here you go. Here's the acceleration of the object, and I'm going to write that. So here you go. The velocity vector, consequently, is going to be what? Is going to be V naught plus a t, just like before. Just like before, but now, the a is going to be a vector, okay? V naught plus a t. Make sense? I didn't finish that. What you see right in here is in reality two equations, okay? This is a vectorial equation only. And what you see right in here is in reality two equations. Let me show you what does it mean. Here you go. I'm gonna get this. Is one equation along the x-axis and another equation along the y-axis. Here you go. I don't need that. It's gonna look like, I don't need this guy either. You can rewrite that as being, here you go. Vx is going to be equal to V naught x uniform motion, constant velocity, okay? And Vy is going to be given by V naught y plus, not plus, but minus gt, constant acceleration. That's what it means. That's one way of writing down that equation. Okay, I'm going to write it in a different way now. Here you go. Another way. Here you go. That's one way of writing this equation. Okay, but I can here write that in a different, in another way. We can write that down as being, V naught x along the x direction. That's what this guy is all about, right? V naught is V naught x in the x direction plus what? V naught y in the y direction. And then we have to deal with this acceleration here, right? Just like we had before. We already have it written there. Here you go. I put the A acceleration vector right in here. And, just get the x and y components together. Okay, here you go. I'm running out of space here, so I'm going to put the y hat in evidence. So what you see right in here is exactly what I wrote right in here. Okay, constant velocity along the x-axis, constant accelerated motion along the y-axis. And what does it mean in terms of the path of the particle? Okay, in terms of the path of the particle, it means the following. Here you go. It means that this particle is moving with constant velocity, right, along the x-axis. As time goes by. That's the motion diagram of the projectile. Illustrations are easier to visualize than formulas, right? That's why we do that. Here you go. Oops, what's going on here? Okay. Did you get the idea? Okay. Constant velocity along the x-axis and constant acceleration along the y-axis. How would that look like? Initially, you are going to have this part have a big displacement, right, in the vertical direction. But as time goes by, the particle decreases its speed, okay? And the spacing between them becomes smaller and smaller, right? Can you picture that? So here is let's say a t equal to 0, and here is a t equal to t1, okay? So when I'm going to erase this guy here so it doesn't get in the way. So the resulting position of your object is going to be this point right here. Vx at t1, Vy at t1 as well. I'm even going to try to make, leave this way for now. A little bit later, this particle is going to be here. corresponding to the y position and the x position, right? A little bit later, it's gonna be somewhere around here. You go. And I can even show the coordinates, the lines, right? That document the position of the particle. Go. You go right in here. Next one, right? And not only for the x position, but for the y position as well. 1, 2, 3, 1, 2, 3, right? T1, T2, T3, T1, T2, T3. We have this other one right in here. And so on. Okay, so if you do everything in the right way, you're gonna get a parabola for this projectile, parabolic motion for this projectile, something that we can prove as well in the classroom, okay, with the equations. Got the idea? So those are the equations of motion right here. Okay, that's for the velocity, yeah? The equation of motion for the velocity. Let's write that down here. A, right? So whatever we learned in 1D motion is being applied to 2D motion. There's only two of the equations of motion. I still need the position, right? I still need the position. Okay, we know that for uniform motion, you already know that for uniform motion, the position is going to be, uniformly accelerated. And I can here even, here write like a vector as well. Here you go. Vec, right? R naught, right? Remember the one-dimensional equation. The one that, let me just write down the one-dimensional equation for you for accelerated motion and for uniform motion. T, right? That's the one dimension. That's the one-dimensional counterpart. And if you have an acceleration, you're going to have a half term here, a t squared, right? So the same type of notation is prevailed here in this vectorial equation. Okay, so we have x naught, we have the vector position, right, which is related to the x position. We have the initial position of your particle that's related to the initial vector position. We have also here we have initial velocity in one dimension. We write that as being initial velocity as vector. And finally, we have half a t squared. Okay. And now it's just a matter of putting the right parameters in there. If I'm dealing with this type of situation in which the initial velocity is at the origin, okay, if the initial position is at the origin, right? If the initial position is at the origin of the coordinate axis, then R naught is going to be 0. R naught is going to be 0. And this guy, disappeared. In the case of your initial velocity, you have an x component for the initial velocity. I need this one here. You have an x component for the initial velocity, and you have a y component for the y component of the velocity, of the initial velocity. Notice that we have an angle theta. Okay, we know both the magnitude of the initial velocity and the angle that the velocity, the initial velocity makes with the horizontal. So here we go, going back there. So now I'm going to apply that here. Here you go. The initial velocity. Let's see here. I'm going to get, here you go. I'm going to repeat this one. That's the initial velocity. Put parentheses here. Okay. Let me do another step here. Okay. Are not the initial velocity is broken down into two components. That is step by step. Okay. And the acceleration has a single component. Which is, I'm going to write it go. Like here, that's the one I want. Okay. Grouping, everybody, all the x and y components in a single parenthesis, right? We're going to write that in a different way. Here you go. This guy is, I gotta put the t here. First, I gotta put the t here, right? Expand this equation. When I expand the equation, I don't need the parentheses anymore. I'm going to get rid of the parentheses that we have here as well. And it looks nicer if I put the t square, if I put the y hat at the end of this term of the equation. Okay. And now we have this equation. Okay. This part here is uniform motion. This part here is uniformly accelerated motion. And here writing that, we have, here you go, breaking down the vector r, right, into x and into y. X and y position. Okay, so now we have those equations of motion. Let's see here. This one. Summarizing, right? That's the equation of motion here that we end up having. The important thing is that the motion along the x and y axis are independent of one another. Okay? That's for the case in which we neglect air friction. Throughout here, we're neglecting air friction all along. If I want, I can rewrite my b naught x in terms of the sine and in terms of the angle theta. Okay, and that's what I did here. Along the x direction, right? We have v naught cosine of theta. That's another way of writing the same thing. There you go. Vx and Vy. And that's what we have here. V naught cosine of theta, V naught sine of theta minus GT. And then we have for the position X naught, well, the X naught is usually 0, right? Because we can put the projectile the origin of the coordinate system. And the Y naught also is usually 0. Okay, so let's see here. Let's see if I have a better. So projectile motion is a combination of constant velocity along the horizontal direction and constant acceleration along the vertical direction. That's what you have to memorize to solve this problem. And now we can start playing some games with this, with this type of equation. Okay, so we have repeated things here, right? Oh, here you go. Here's a different way of writing down the equations of motion. Different way we can here write the equations of motion in terms of their components. Okay, and that's what we have here. Just a different way. X and Y. And also I put, instead of putting V naught X, I put V naught cosine of theta and V naught sine of theta. Okay. Having said that, now we can play some games with those basic equations and find out, for instance, what's the functional dependence of Y in terms of X. Okay. You already know that it is a parabola, but the idea here is to prove mathematically that it is a parabola, okay? So what would be the functional depth? Right now, you have what we call a parametric equation, okay? Let's write it down. Right now, we have what we call a parametric equation, which is what? What's the parametric equation? Parametric equation is something in which X is given as a function of another variable, in this case, T, right? See that? That's the variable T. This guy is constant, the theta is a constant as well. And the same thing can be said about the Y. The Y parameter. It's also given in terms of a parametric constant, a different functional relation, right? Vx, you can also state the same thing, yeah. You can also state the same thing. You go here, it's going to be given H as a function of the parameter T. Okay, and Vy similarly. Vy too can be is written in a parametric format. I'm going to put K here. Okay, and so on. But what about writing Y as a function of X? Okay, how can we do that? Well, there's a way to do that. Well, if you find out what's Y as a function of X, then you find out what's going to be the path of the projectile in the XY plane. Okay, and we can prove that's going to be a parabola. Parabolic one. Let's do that together. Okay, challenger. Find how Y as a function of X. Find what is Y as a function of X. Okay. In other words, find the functional dependence of Y with X. Okay. We want to find this relation because we want to know what's the path of the projectile in the 2D space. How do we do that? How do we do that? Huh? The answer is simple. We eliminate the parameter T from the original equations for X and Y. That's how we do it. That's the trick. Okay. So here you go. Let's start. I'm gonna do only for x and y. Okay, there's no need to do for vx and vy. So how do we do it here? I want to eliminate t. What does it mean? I want to eliminate t. Okay, so in order to eliminate t, we must write it in terms of the other, in terms of one of the variables, x, either x or y, either x or y, either x or y. Okay, so we have this option here. We can write t in terms of x, or you can write t in terms of y here. But if you look at the equation, what's easier to do? What is it easier to do? Is it easier to write t in terms of x, or is it easier to write t in terms of y, right? So the question is, what is it easier to do? To write t in terms of x or in terms of y, right? Think a little bit about that. Note that this equation here is linear, and this one here is parabolic. If you were to write t in terms of y, you would have to solve the roots of this equation, okay? You know, minus b plus and minus square root of delta over 2a, okay? And you're gonna get, it's gonna become very complicated. So it's easier, you know, to write t in terms of x, because the first equation is linear. It's linear, comma. It's easier to write t in terms of x. Okay. So let's do that. Here you go. I'm gonna put the v0 cosine of theta on the other side here, right? That's the first step. I'm gonna do step by step, right? I'm gonna write down t in terms of x. What do I have to do to write t in terms of x? I have to pass those two terms to the other side. Okay, so that's what means eliminating t. Eliminating t from the equation means writing t in terms of the other variables, okay? That's what means eliminating t from the equation. In order to eliminate the equation, you must write t in terms of the other variable. Now, what's the next step? Well, the next step now, remember, I want y as a function of x. Right now, I have y as a function of t. How do I get y as a function of x? All I gotta do is substitute this t right in here. I'm gonna boldface it and right in here. And right in here. Okay, so let's do it. Substitute it here. I'm going to put a parenthesis, and I'm going to put a parenthesis here as well. Okay, let's now work out this equation. Let's see if we can make it look nicer, right? Now I'm in my way of writing y as a function of x. I have like a 50% of the job done. See, now I have only x here. I have only x here. Let's continue writing it. Here go, this v0, no, is going to cancel out with the other v0 in the parentheses. Okay, here you go. v0 cancel out with v0. Then we end up with sine divided by cosine, right? Then we end up with sine divided by cosine. And then I'm going to do this one here. In the next step, I will bear with me. The next step, I will rewrite my sine over cosine. The cosine here is going to be squared because of this square outside the parentheses. Okay. And now I'm going to rearrange the equations. Here we go. Sine divided by cosine is what? It's tangent, right? Tangent of x. And then what else can I do here? You know, the best way to write this equation, you know, to make it look better is to put the x squared outside here and put the g upstairs. Why do I do that? I'm doing that so you can visualize this equation more readily. Okay? Remember that tangent is a constant, V0 is a constant, G is a constant, theta is a constant. Do you see a parabolic equation there? Right? Do you see a parabolic equation there? If you do not see, we can go ahead and define, let's say, B as being tangent of theta. Okay? Defining, here you go. B as being tangent of theta. And C as being minus this G over 2V0 cosine square. We can here write that as, here you go. I'm going to do even better. Instead of writing C as a minus, I'm going to put C as equal to this guy here, right? And notice that G is going to be greater than 0. V0 square is greater than 0. Cosine square is also greater than 0. Okay? So when I do something like that, instead of having a positive sign in the front of C, I'm going to have a negative sign in front of it. So now notice that this relation between y and x is a parabolic one. Right? Not just a parabolic one, but the parabolic one with the concavity of the parabola downwards. Concavity of the parabola downwards. That's what this negative sign is all about. So I prove to you the path of the projectile is a parabolic one. Okay, I can erase that now. Concavity down. What else can we talk about? You know? Let us solve another example. Another example. Another example, okay. Given a projectile is propelled with a non-initial velocity, magnitude, and angle, and direction, find the highest point the projectile reaches. Okay. So here you go. So we have, let me illustrate it here. I didn't finish illustrating that, right? Let me illustrate that here for you. And, let's see. I'm not gonna draw everything. Here you go. I'm gonna do like that. Let's see if we can. I can make it look like a parabola here for you. Yeah, I think I can, right? Can it look like a parabola? Not exactly a parabola, but the best I can do, right? Let's see. Yeah, getting there, right? Good. So what we want to know now, we want to know the maximum height. Okay, the maximum height that the projectile reaches once we propel them with a given initial velocity. Okay, here you go, like that. It's just a matter of finding out, okay, so given the initial velocity, given the motion of the projectile is a 10 meters per second, has an acceleration of 10 meters per second square, right? Find the highest point. So I want you to think about that. Okay, it's 9:43 right now. Okay, let's take a little break now. 15-minute break. 15-minute break. And while you think how to do that, while we're in the break, think how you are going to solve this problem. While you are in this break, think how you're going to solve this problem. Right? Any questions? Am I missing anything here? Okay, I'm gonna pause the recording and remind me when we are back, whenever we are back from break, remind me to turn it to start the recording again. Okay, I'm back here and let's take attendance. I should have taken that before, right? So here you go. Jade, are you there? Jade Bisquera, right? Jade. I'm see here. That you're okay. You're there. Good. Thank you. Vanessa Bonilla.
Here.
Thank you. Maquin Curto. Thank you, Maquin. Ashley Diaz.
I'm here.
Thank you. Fisher Dawn.
Here.
Thank you. Blessing.
Here.
Thank you, Erica Fajardo. I don't see Erica here. Janet Garcia.
I'm here.
Thank you. Raymond Garcia. Thank you, Raymond. Donovan. I don't think Donovan is here anymore. Oh. Lily? I can't hear you, Lily. Your mic is on, but I can't hear you.
She typed that she's here.
Yeah, I know. Okay. Let me turn off her mic. Good. Okay, Michael Asid, are you there? Good, thank you, Michael. Wendy Hernandez. I don't see Wendy. Joshua Jimenez.
I'm here, Professor.
Thank you, Bethany.
Here.
Thank you, Luis Latisa. Gabby, right? I don't see Gabby here. Ana Lopez. Thank you, Basilio Lopez. Thank you, Basilio. Bahag. Thank you, Daisy Mariscal. Janet Garcia. Okay. Where's today? Alejandra Marmolejo.
I'm here.
Thank you. Amarilis Mejia.
Here.
Julissa Molina. Okay. Yesenia Montes Rodriguez. Hi, Yesenia, are you there? Okay, I'm gonna put a star here for Yesenia. Mary Okeki.
I'm here, Professor.
Thank you. Who is that?
Mary Okiki.
Oh, okay, good. Thank you, Okiki. Thank you. Ryan
Oh,
Ong.
thank you.
I'm here.
Okay. Arthur Pacheco.
I'm here.
Next is Jennifer Perez.
I'm here.
Lebilud Ponte. Thank you. Lydia Rosa Buencosta. Thank you. Pedro Ruiz. I don't think he's here. Donia.
Here.
Thank you, Donia. Elika Buffet.
Here. Here, Professor.
Thank you. Brianna Valencia.
I'm here.
Mia Villalobos.
Here, Professor.
Thank you. Justena Youssef.
Here, Professor.
Okay, let's see. Arika, are you there? Arika and Kelly? I don't think they are. And 29, 30. Okay, good. We have. Okay, so you have time to think about this problem, right? Solving problems in physics is about finding out what information that you have that can be used in the problem. Okay, that's what it is. So if you have a projectile's initial velocity naught and a launch angle theta, here you go, right here. What's going to happen at the top of the trajectory of this projectile? Okay. Well, let me illustrate here for you what exactly is going to happen. You know that the height is going to be maximum, right? It's a parabolic motion, and the maximum height is going to be exactly at the middle of the whole trajectory because the parabola has symmetry. But then there are other things too. You know that the velocity here, velocity vector of the projectile is going to be always tangent to the path, right? So here you go, at this spot, the velocity is going to be tangent here, right? And on the top of that, the velocity is going to decrease because there will be a acceleration component that's going to slow down the velocity of this projectile. So at the top of the trajectory, what's going to happen to the velocity of this at the top of the trajectory? I'm exaggerating here, okay? So let me see. At the top of the, let me put a longer vector so you can see better. At the top of the trajectory, and I'm going to put a different color as well. The projectile is going to have only an x component of the velocity. The y component of the velocity is going to be 0. Okay? So the key to solving this problem is to find out the instant of time in which the Vy, the y component of the velocity, is 0. Okay, that's the picture that you have to have in mind. Okay, here goes. Solution. A projectile achieves its highest height whenever the y component of its velocity is 0. Okay. Then you go back to your equation. Here you go. Look at the equation for v sub y, and you will be able to find out what t is, how long it took for the projectile to reach that position. And that's what I did here. You know, Vy equal to 0. I'm gonna solve for t. Okay. Solving for t, you get this value. And then what do we need? Okay, it took this amount of time to reach the highest point of the trajectory. So what do you have to do? To find the highest point, the value of the highest point of the trajectory, you substitute this value here for t in this equation here for y. Okay. So the key piece of information here is this one here, y component of the velocity. That's the key piece of information. If you don't know that, you couldn't solve this problem. And now substituting there for y, you know, put t here, right? T for highest point. T for highest point. Okay, we expand the whole thing. Let's see here. Yeah, V naught is square, right? V naught combined with another V naught. G sine combined with sine becomes sine square. Half of G, we have to square this term here, V naught square over G square sine of theta is square. And what we get, here go, this one doesn't change. This one you can cancel this G with this other G. And then look what we get. We get V naught sine square over G minus V naught sine square over 2G. And that's gonna be the maximum height, okay? So ideally, we should put like that, okay? Oops, maximum height, okay? Here is T for maximum height. I'm gonna put it T for maximum height. Okay. The moment I make Vy equal to 0, T becomes T for maximum height. Let me see here. Okay. Okay, and so we can now, come up with some interesting problems, right? Given the velocity, given the value of the launch angle, right? What's going to be the maximum height of your projectile? That's one type of problem that you can see out there, okay? Another, okay, so here you go. Let me just summarize what I have been doing so far. Summary, equation and projectile motion. Projectile motion. Well, we did equations of motion. Okay. We find the equation for the path of the projectile. And that's gonna be what? Y equal to F over X of X, okay? Maximum height of a projectile. And now we're going to do another different type of problem using those equations of motion of the projectile. It's going to be the range of the projectile. What's the range of the projectile, right? The range of the projectile is the distance it impacts the ground is the distance from the launch point to the point where it impacts the ground. Okay. So if I'm going to illustrate the range of the projectile, the range of a projectile is going to be this distance here, from here to this point here, where the projectile impacts the ground. Okay. And just like before, you have to apply the conditions for the projectile to reach this point here. Okay. What is the condition? So here you go. That's the example, right? I'm treating it as an example. A projectile has initial velocity v naught and launch angle theta. Find the maximum range of the projectile, the horizontal distance where it impacts the ground from the point of launch, from the launch point. The launch point. Okay, so a projectile is going to reach maximum range whenever the its y position is going to be equal to what? It's going to be equal to 0, right? So that's the condition for maximum range. Actually, it's condition not just for maximum range, but it's also the condition for the initial position of the projectile, the initial height of the projectile. So the condition that you have to use, like before, right? In the previous problem, the condition that you had to use to find the maximum height was y component of the velocity equal to 0. And now maximum range, y component of the position is going to be equal to 0. That's the key piece of information. Okay, so you can do that. There's more than one way of doing that. You can, for instance, use that equation for y as a function of x. Okay, put y equal to 0 here and solve for x. That's one way. Okay, so here you go. That's the equation. I don't have it here. Here you go. That's the equation here that we derived before. Or another way of doing that would be just go do the hard work, right? You put y equal to 0 here, solve for t, and plug t here into this equation to get the range. Okay, either way would work. So here you go. We put y equal to 0 here. We get x tangent of 0 minus g 2v naught square cosine square theta x squared. Remember that we have a quadratic equation. This quadratic equation has two roots. One of the roots is x is equal to 0, which is exactly what my drawing states, right? The x is equal, you don't want the solution. You don't want the solution because you already know that x equal to 0, the position of the projectile is 0 as well. You want this other solution, okay? One solution for that quadratic equation, the other solution for the other quadratic equation. So that's the solution that you want. So here you go. How do we do it? Just putting x in evidence, we are left with this term here that must be equal to 0. Tangent of theta minus g 2v naught square cosine square of theta, right? Make it equal to 0 and solve for x. X in this case is going to be R max. Okay, there you go. That's what I get. V square, V naught square over G 2 sine of theta. That's going to be the range of the projectile. Okay, note that the highest the speed of the projectile, the higher, right? Not the highest, the higher the speed of the projectile, the longer its range. So the next question is, what is the launch angle for the longest range. Okay, at this point in time, you should know that, right? Here's the equation for the range. Different angles of launch for a given speed is going to give you different ranges. Okay. So, but what would be the longest one? Well, the longest range would be that one in which sine of 2 theta is equal to 1, right? Sine of 2 theta equal to 1. Now recall that, you know, in order for sine of this angle here, 2 theta, to be equal to 1, it means that 2 theta must be equal to 90 degrees. Make sense? Right? And once you solve this problem, you get that the longest range that you are going to achieve with your project is going to be 45 degrees. Okay. Okay, so those are the type of, that's here the quick review, okay. That I want to do for projectile motion, and let's go back here to the motion. What I want to do now is to start chapter 4. Okay. By the way, I prepared homework for chapter 3, but did not. But I couldn't publish it. I didn't publish yet. Did not publish yet. Okay. So later on after the class, you know, go there. Later on after the class, go to Wiley Plus and check for chapter 3 homework. Okay. And here is let me see, I want it here. No. Wiley course resources, right? So we cover, here's chapter 3, displacement, velocity and acceleration, equation of kinematic in 2 dimensions, projectile motion. You don't have to worry about relative motion, okay? So what I want to do now is to talk about chapter 4, start with chapter 4. Okay? Concept of force and mass, Newton's first law of motion, Newton's second law of motion, third law, and types of force. Okay, that's let us start with chapter 4 now. It is in chapter 4, you know, in chapter 4 when we start using the idea of force. Okay. Okay, force, you know, is defined, as you saw before, as either a push or a pull. Okay. This idea of force has been around for a long time, okay? This idea since antiquity. This idea of force has been around since antiquity. So it's not recent. Ancient Greeks already knew about. They were already using this idea of force. Okay. And what this chapter requires, is for you to visualize the forces applied to an object, okay? That's what this chapter requires. And in order to visualize, you have to make drawings, come up with drawings. Here you go, let me go here, not this one. Okay, here you go. Okay. So here you go. We have what we have here. We have a block. Okay. And this block here is at rest. Velocity is equal to 0. Can you see that? Okay. If the velocity of the block is equal to 0, it means that the surface that you have right in here is preventing the block from moving downwards, right? Can you picture that? So let me do an even better illustration, okay? So here you go. Let's say that this block doesn't have any support whatsoever. Let's say this block has no support whatsoever, right in here. By no support whatsoever means what? Means that this block must be falling in space, just like a projectile, right? So we know that by experimentation. Okay, and how do we explain that? We explain that this block is moving because there is a force that the Earth applies to this block, to this object. We call this force the force of gravity, or the weight. So that's the first force that you have to know. Weight of the object. Of an object. That's why the object moves, because you have this force applied to it. Okay? Therefore, here you go. The first force you have to know is the weight of an object. Okay? If you are at the surface of any planet, you will have a weight. Okay? Which by the way is related to the acceleration of gravity in the following way. So weight, write that down as W, is G, right? It's directly proportional to G, but it's also directly proportional to the mass of the object. You know, M is the mass of the object, which is a measure of the amount of matter that the object has. Okay? Here on the surface of the Earth, we have a given G. At different planets have different acceleration of gravity. Okay, so the weight might differ from one planet to another one, you know? So that's the first force that you have to know. The force of gravity, the weight. Now we go ahead and put this block on a surface, just like I put my cell phone right at the surface of my hand, you can see that this object is not going anywhere. Why is that? There's a reason for that. Okay, so every object is going to have its own weight. Okay, so let me put that here. Here you go, weight. And then when I look at this object, it's not moving. But it is not moving because there must be a second force applied to this object. The second force is what we call the normal. A force that the surface applied to the object. Okay? And that's when we come up with the first Newton's law, first law of Newton. First law of Newton. First part, I'm gonna even go further than that. I'm gonna say first part of the first law, first Newton's law. Okay. If an object is at rest, G equals to 0, then the net force applied to this object is 0. Okay. Now we are talking about laws, right? Remember the basic concept, the core concepts of physics? Right? We talked about quantities, we talked about definitions, and now that's the first law that we ever see in physics, first Newton's law. If an object is at rest, then the net force applied to this object is 0. In the case of the example that I put to you, okay, in the case of the example that I am illustrating right now, we have the forces. We have the weight, forces, comma, the weight and the normal. So Newton's first law states that, you know, the net force, what's the net force? Net force is going to be the sum of all forces, the weight plus the normal is going to be 0 if the object is at rest. Okay. And there is more. Force is a vector. So we have to put the vectorial sign there at the top of the force. Okay. Not just at the W, but also at the N. Okay. If you already know what the mass of the object is, right? Here you go. I'm gonna put an X and Y axis here as well. I didn't do it. Let's see if I have it. No, not this one. X axis. No, Y axis first. Here you go. And then the X axis. X and Y axis. We can write down the weight as being what? Minus mg in the y hat direction. Oops. Y hat direction. Yep. Why this one here? Here you go. Y hat direction plus n is going to be equal to 0. Make sense? Okay. Here's the y-axis. The unit y is upwards. The weight is downwards. The weight always points towards the center of the Earth. Consequently, the weight is going to have a negative sign when you write that in terms of the y hat. You go y-axis here. And x-axis here. So now we can solve this problem just the way we solve any algebraic equation, and we find that the normal is going to have the same magnitude as the weight, but opposite direction, right? So compare this normal with the weight. So that's the type of problem that we are going to be solving, okay? And what you see here is the samples of all problems that you're going to see out there. Then the problem can become a little bit more difficult, okay? We can come up, for instance, with, we can rest an object over a wall, okay? And if you find out that there is this normal force being applied to this object because the wall is applying, if you find that the wall is applying a force to the object to the left, what does it mean? You know, it means that there must be a third force applied to the right. Okay, so here in this specific case, the object is at rest. Let's do that. Here you go. Object is at rest, right? Object is at rest. We know that there is a normal force N2 applying the horizontal direction in the object. One possible problem. Find all possible force that this object is subjected to, okay? Given, let's write that down here. Another example. Given our block is in contact with a wall which is applying a force to the left, comma, find, given that our block, given that a block, okay, is at rest over a horizontal surface and in contact with the wall, comma. Also, knowing that the wall is applying a force to the left on the block, find all possible forces that the block is subjected to. Okay. And applying force to the left of the block. I call this force N2. Okay, so if the block is at rest and we have this force to the left, it means that we must have another force applied to the block from the right, from the left as well. This force I call, let's say, N3. Okay. On the top of that, we know that every object on the surface of the Earth is subjected to the force of gravity that we call the weight. Okay, you go, it always points towards the center of the Earth. I call that the W. Oh. But because the object is at rest, we must have another force that I call N1 that's countering the weight. Okay, so here you go. So those are all the possible forces that this block is subjected to. Okay. When you sum those forces along the x and y axis, we must have a net force equal to 0. So, along, we can say that along the x axis, N2 is going to be equal to minus N3. Going to be equal to N3. By the way, it's not N3, it's minus N3. Okay. And just like before, the weight is going to be equal to minus N1. Okay. So here you go. First thing you have to know, let me just summarize here. First thing you have to know is the definition of force. A push or a pull? Or a pull? A push or a pull? Next thing you have to know. Every object nearby the surface of the planet has a weight which points towards the center of the planet. And the next thing you have to, and then first part of Newton's first law. An object at rest has a net force of 0. An object at rest is subjected to a net force of 0. Okay. Knowing all of that, you can solve any problems related to an object, any force problems, right? Related to an object that is at rest. Okay. So those are the important pieces of information here. What else do we have here? Let's see here. One more thing, right, that I didn't mention. Oh, by the way, the unit, okay, the unit of force. I didn't tell you what the unit of force is, right? But the unit of force is the Newton. Soon we're gonna learn that the Newton is equal to kilogram times meter second square. Okay. 1 Newton is equal to that. It's a composite of those 3 units, of the 3 main units. Okay. What's next that you have to know? Okay, so one more thing you have to know. Okay, there's another type of force. Right? So here you go. So you learned about two types of force. We learned about the following forces. Weight and normal. Okay. Normal is a force that surfaces apply to an object. But there are more. There are more forces. Another one is called tension. We abbreviate it by the letter T. Okay, so I'm going to illustrate here. Here you go. What did I do here? I attached my block to a string. Okay, just like my book here. I'm going to show you my book. Let me stop sharing momentarily. I have a string right here attached to my book. Hopefully it's not going to break. Okay. So this string here is applying a force to the book. We call this force the tension, right? So, and we abbreviate it by the letter T. Here you go. The tension can take all sorts of directions, okay? Can be a horizontal, can make an angle, okay? And if this block is at rest, and I'm applying a tension to this block, it means that must be another force being countering this tension of the block, the tension force applied to the block. In this specific case, it's fair to, to assume that what we have here is going to be a force of friction. And this force of friction has another name too, has a specific name. It's called the force of static friction. Okay, so let me give you an example, right? So here you go. I have my cell phone here on the surface. Okay, and I'm going to apply here you go. I'm going to apply a force to the cell phone. If the cell phone doesn't go anywhere, that's because there must be a force acting against my applied force here. It can be a tension or can be even a normal force, the force that my hand is applying to the object. This force, we call it the force of friction. And because the object is at rest, we call it the force of static friction. Okay, so here you go, let's go. Tension, tension T, here you go. There is a force of friction. And there are two types of force of friction. Force of static friction, usually represented by the lowercase fs, and force of kinetic friction, represented by F sub k. Okay, just like the name suggests, force of the static friction is that force that you have whenever the object at rest, Kinetic friction, object moving. Object moving. Okay. Now we have a different situation here. Okay. Suppose now you have this tension being applied to the object, right? Let me, okay, I'm gonna illustrate it better with a string here. Okay, here you go. Let me stop sharing for now. You can see my object here, right? And now you have a string right here. At this very moment, I'm applying attention on this object with my hand. But the object is not moving anywhere because we have a force of static friction. Static friction. Net force is equal to 0. But you also have a different case, a case in which you apply attention, the object moves, but the object moves with constant velocity. We have the situation as well. If the object is moving with constant velocity, we have the second part of Newton's law, Newton's first law of motion. Okay, so let's write it down here. When an object moves with constant velocity, okay, then we have the second part of Newton's law, first law of motion. First law of motion. Okay. Well, which is very similar to what you saw. And now, here you go. Not first part now. Now, Newton's first law. An object. Let's do this first part, right? Here you go. Now I'm going to write down the second part. Second part of Newton's first law. Second part of Newton's first law. An object moving with constant velocity is subjected to a net force of 0. And vice versa, by the way. And vice versa, by the way. If the net force is equal to 0, the object is going to be either at rest or moving with constant velocity. Combining those two laws, right? Combining the first and second part of Newton's first law, parts of Newton's first law, we have an object moving either at rest or moving with constant velocity is subjected to a net force of 0, and vice versa. And vice versa. Vice versa means if the net force applied to an object is 0, the object will be either at rest or moving with constant velocity. Okay, so that's something that you have to memorize. Okay, this is a law, you know, this is a law, and because it's a law, and because of that, it cannot be derived mathematically. Okay, so now you have our first law, the first law that you are learning here. We started, remember, we started with the basic quantities, right? That's the, then I introduce you to the primary definitions, you know, core ideas of physics, right? Basic quantities. I introduced you to the primary definition, and now, you know, I'm introducing you to the first law of physics and the laws of physics. Okay, so let's see. Okay, V, and by the way, greater than 0, equal to constant in this case, okay? Okay, which other forces do you have out there? Okay, which other forces do we have out there? Okay, so let's start making our list, right? Here you go. Weight that you have to know, normal. You have to know tension, force of friction, two types of force of friction. And then there are others too, right? The weight is like a gravitational force, also has a name of gravitational force. Okay, there's the force of thrust. Okay. If a rocket, a rocket moves because of the thrust of its engine. That's one type of force as well. We have air friction, force of air friction. Even better, not air friction, but fluid friction. I'm gonna, can be either air or liquid, right? If we put your hand, if you're driving your car in the freeway at 60 miles an hour, right? If you put your hand outside the window, you're going to see that there will be some force due to wind colliding against your hand, right? That's another force as well. Is air friction, the force of air friction. And those are the forces. Let's stop. There will be more forces, okay, but let's stop it right now here. Let's play with these forces with some problems and some examples, right? And but let's have our break first. It's 10:55 right now. Let's see, break. Any questions before we go for the break? Break till 11:10 a.m. Okay. So I see you shortly. I am back here, and I want you to, let's change gears a little bit here. I want you to check a website that we have here. Go, let me share the screen so you know what I'm doing, okay? Here you go. There is this nice website, and it's called the FAT simulator. Okay, it's we have several simulations in physics let's see here. Oh, at the University of Colorado. Okay, simulation FAT. Oh, it's in Portuguese. This one shouldn't be in Portuguese. Let me see. Yeah, let me get that in English for you. Yeah, okay, so that's the site. Let me send you the link for the site. So you might want to play a little bit with this simulator. Link for simulation in physics. Okay, so interactive simulations for science and math. What we want is physics, right? You scroll it a little bit down, go into physics. You have a bunch of simulators here. What we are seeing right now is motion. Later on, you're going to see these other topics here. Sound of waves by the end of the semester. Okay, work and energy is going to get to see that soon. You can see that we have vector addition. Okay, so if you want to practice all those concepts that we are working on, take a look at those simulators. What we are doing right now is this one here, forces and motion. Okay, so let's see one by one. Go. Normal mode is going to be waves at the end of semester. Collision lab is going to be at the middle of the semester. Energy skate park is, we're close enough to do that. It's going to be later on. Vector addition, we already did that. Okay, and gravitational forces, masses and springs, we're going to see all of that. The pendulum, you're going to see that too. Oh, projectile motion. We just finished projectile motion, right? Let's take a look in this simulation here. Here you go. Gonna play. Okay, so here you go. Introduction. Let's see. Okay, so what we have here, we have the cannon, right? We can change the height of this cannon, and it's going to propel a projectile. Okay, we can change the speed of the projectile right in here, see that? And let's say, boom. See that's the path that the projectile takes when you launch in the horizontal direction. You can also do that problem that we did before, right? In which you launch the projectile at a given speed, boom, right? And look what happened. Here's the range of the projectile, right? The projectile acquired its initial speed right inside of the gun, of the cannon. We can increase the speed. What's going to happen to the projectile? Oh my goodness, it flew all the way down. You can see that the range is much higher, right, than the other one. That's because the range, changed with the square of the speed, right? If I'm going to, let's decrease it a little bit more. Okay, yeah, we get another range, and so on. Is a parabola. So we have this type of projectile motion. We also have this type of projectile motion, right? That you can launch the projectile in the horizontal. And you can have this type of projectile motion as well. It's more difficult to treat mathematically, okay? I have treated that before. I have treated that before in my labs. Note that the range in this case here is going to be different than the one we treated before, okay? And the projectile can also be sent upwards, right? That's that for the projectile. What else we seen? Have you ever seen that before, by the way? I want to hear from you folks. Have you ever seen that this simulation before? No? Okay. So here you go. Right now we are doing this, we're covering this topic here, forces and motion. Yeah. Okay. Let's take a look. Here you go. Net force, motion, friction, and acceleration, right? Here you go. So we can apply a force to this little cart, right? So here you go. If I have this only guy here pulling to the left, you're going to have a summation of the force is going to be to the left. The software assign a force value for this little guy, right? For this guy. And this guy like 150 newtons. Okay. If there is no force applied to the right, what's going to happen to this cart? It's going to move to the left. Okay. And notice that the speed is increasing, okay? Notice that the speed is increasing. Similarly, if I put the same, another guy that's going to apply the same force, net force is 0, right? And the speed is going to be 0 as well. Okay, that's the first part of Newton's first law. Let me see if I can give them a little push. Let me see. Okay. Did you see what I did? Net force is equal to 0, but the cart is still moving. See that? That's the second part of Newton's first law. Let's do that again. Return, right? So what did I do here? Right now, the net force is equal to 0. The cart is at rest because the net force is equal to 0 and the cart is at rest. It is going to continue at rest. But if I apply a little force here, a little additional force, 50 newtons, right, to the right, make it move, right? And then I withdraw the force of this guy. Look at the speed, right? What's going to happen? It's going to move its constant velocity. The velocity doesn't change, right? Let's do that again. I'm going to apply a little force here, 50 newtons. I'm going to get it going. The cart is going to accelerate a little bit, and now you will stop accelerating. The speed is going to be the same. That's net force equal to 0. Velocity is constant. The cart, the object will continue to move its constant velocity. Okay. So we have this one as well. Let's do friction. Let's do friction. Here you go. Force. And I'm going to apply some friction here. Apply some force to this guy. Here you go. 1 Newton. I'm applying 1 Newton of force. Okay. And sum of the forces is 0. Why is that? Because there's some friction there. Let me increase the friction a little bit more. Let's see if we can. Yeah, that's because it's just 1 Newton. Let me see. Let me increase a little bit more. We cannot see the arrow here. Okay, now we can start seeing the arrow. See that? The arrow was so small. Now we can start. Here you go. That's the applied force by this guy, right? But because the force of static friction is so large, the net force is 0. Okay. So eventually, this force of friction is called what? It's called force of static friction, right? Eventually, the applied force is going to be greater than the force of static friction. That's how the force of friction works. the force of static friction works. It has a maximum value, okay? Eventually, let's see. Oh yeah, right in here at this point. Right in here at this point, around here, the applied force becomes greater than the force of static friction. See that? I don't know why it goes back. Interesting. It goes back. Okay, so let's keep increasing, keep increasing. Here you go. Force of friction. Applied force. Let's see. Keep. Oh, now we got there. Now we have a force to the right. I'm going to decrease the applied force so we can have a net force equal to 0. Okay. When you get net force equal to 0, the object is going to move with constant speed. See that? Net force equal to 0, constant velocity. That's Newton's. Net force equal to 0, either constant velocity or object at rest, right? And the opposite also works as well. If I take a look here, if I increase the applied force, then something else starts happening. Take a look at the speed. I'm increasing a net force, sum of force, it doesn't give you the value. Notice that the speed is increasing little by little. That's because I didn't apply now. Okay, now I'm applying some force here. Values, okay, 14 newtons. See the speed is increasing. Now that the net force is different of 0, the speed keep on increasing. We generate an acceleration. That's Newton's second law. Let me go back here to the net force is equal to 0. Okay, here you go. Net force is equal to 0. Speed constant. Okay. If I increase my frictional force here, and I can do that, what do you think is going to happen? Here you go. The object is going to slow down until it comes to rest. Okay, here you go. Notice that the force of applied friction changed its value, and that's how force of applied friction works. Let's write it down. Here you go. So that's the next law that you have to know. Okay. Newton's second law of motion. Okay. Okay. Is an equation. Is an equation. You go. And you write like that. Before I write the equation, let's write it down. If the net force is applied to an object is different of 0, then the object will be accelerated. Okay. In terms of equations, we write this way: net force equal to mass times acceleration. Okay, will be accelerated its acceleration being inversely proportional to the object's mass and directly proportional to the net force. Okay, that one. by the way, the direction of the acceleration is going to be in the direction of the, by the way, the direction of the acceleration will be in the direction of the force of the applied net force. Okay, that's how you write. That's Newton's second law. And we can come up with a simple example. Okay, so here you go. Let me do a very simple, an object of mass m equal to 5 kilograms. And let's see, a net force of 5 newtons is applied to an object of mass equal to 5 kilograms. And that's for 5 newtons. To the right, horizontal net force of 5 newtons to the right is applied to an object of mass 5 kilograms. What is its acceleration, magnitude, and direction? Okay. Think a little bit how you're going to do that. Okay. We have this type of problem. You can find the acceleration from the net force, or you can find the net force from the acceleration as well, provided you know the math. And that's exactly what those simulations do. They apply Newton's second law and they come up with those videos, right? So-called videos. Okay, so here you go. We use this equation here. Here you go. Net force equal to mass times acceleration. I want to know the acceleration. All you have to do is to divide the net force by the mass. Like that. There you go. I can divide a scalar by a vector, right? Mass is a scalar. Okay, and let's solve everything in terms of magnitude here. Magnitude of the acceleration. Magnitude of the net force. Five newtons over 5 kilograms. 5 kilograms. Remember that I told you that the Newton is equal to kilogram meter per second square? It comes exactly from Newton's second law of motion. Okay, so when I apply kilogram meter per second square here in this equation, you know, 5 cancel out with 5, right? Kilogram also cancel out. Let's put 1 here for now. In the next step, I cancel the kilogram, so it doesn't become too overwhelming for you. Here you go. And that would be the acceleration of the object. That's the type of problem that you're going to be able to solve, okay? If I'm going to illustrate it, would be here in my PowerPoint, would be something like the following. Remember, it's a net force, right? Let's see here. I'm going to get this one here. And yeah, the net force should be something like that. Subscript. Okay, I don't need that. I don't need that. I don't need that. Net force. And what else? I illustrate the fact that this object has a mass m. Okay. And we also come up with another arrow here at the top of the object and put the symbol of the acceleration. So I'm showing that the acceleration of the object is in the same direction as the force. Okay? That's how we illustrate it. The acceleration has the same direction as the net force. Okay, Newton's second law. Let's talk about the force of friction. There's more that I want you to know. Let's see if I have an illustration here for the force of friction. Unfortunately, I don't. I have to do that from scratch. Yeah, let me do that from scratch. How does the force of friction behave? Okay, behavior of the force of friction. You already had an idea from that simulation. Frictional force behavior. Frictional force. Okay. So here you go. I'm going to apply a force to an object. And I'm going to observe an object initially at rest. And I'm going to observe, to measure the force of friction, lowercase f. Let's see, I'm going to start at 0 newtons, right? Here you go, start at 0 newtons. Start at 0 newtons. There is no force of friction whatsoever. Okay? So the story goes like that, right? Object at rest. Behavior, here you go, behavior of the frictional force, of the force of friction. Start this object at rest. No force applied. Okay. What does it mean? It means that, okay, because the object is at rest, the frictional force is going to be the so-called force of static friction, okay? Abbreviated by the symbol F sub F. Since no other external force is applied to the object, comma, the force of static friction is going to be 0. Okay. So it's going to be something like that, you know. I start with a force equal to 0, applied force equal to 0. And I, little by little, I keep on increasing this applied force. And the object is still at rest. Because the force of static friction is building up with the applied force, just like you saw in the simulation, right? I'm going to start applying a force. Here you go. Friction 1 Newton, applied force 1 Newton. Friction 2 Newton, applied force 2 Newtons. 3, 4, 5, 6, 7, 8, 9. That's exactly how the frictional force works. Object is at rest, consequently, is force of static friction. Note, see that I have already increased my force to 55 Newtons. 65, 70, 71. Okay, so here you go. I'm increasing my applied force, and consequently, the force of static friction also increases. Okay. Force of static friction equal to the force of applied friction. Object is at rest. B equal to 0. Okay, in this region. Eventually, what's going to happen? The force of static friction cannot keep on increasing indefinitely. Eventually, something has to give in. Okay, let's see where it's going to. Net force is equal to 0. Keep on increasing. See that? 122, 130, 140. Net force is still 0. 150, 156. Eventually, it's going to come to a point that the frictional force cannot keep on increasing. There's a limit of how high a force of static friction can go up. Okay. Oh, I just reached that limit. Okay. So here you go. Stop it. Stop it. It's accelerating now. Do you see that? It's accelerating now. What was 288? Let's see here. I want to do that little by little until you see it. It's gonna come to rest. Okay, stop it. Yeah. Okay, so it should be around what, 200 Newtons? Let's see. 50, 100. Net force is still equal to 0. 150, right? Still net force is equal to 0. 55, 160, 161. That's a lot. We have lots of friction here in the simulator. 69. Keep on watching. 170, 71, 72. Must be around 180, 190, right? This force of static friction. 180. Let's see. Now it's more than 180. Let's see. Keep on going. Keep on increasing. 190. Some of the forces is still 0. 95, 96, 97, 98, 99, 200, not yet. 201, 2, 3, 4, 5, 6, 7, 8, 9. Watch, right? Watch here for the frictional force. Suddenly it's going to decrease in value. 210, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Man, it's taking a long time, isn't it? 24, 25, 26, 27. Okay, 27. It's around 27. Okay, so let's. $27, right? So let's do that again. 50, 100, 150, 200. So we're going to go all the way down to 226. Okay, 226. The object is still at rest. Sum of the forces is 0. Oh, no, it's not 227, is it? Let's see. 227, maybe 228. Net force is equal to 0. Okay, yeah, good. It's 227. So for this specific case, okay, the maximum value of the force of static friction is 227 newtons for this specific case. So genetically speaking, this force of static friction keep on increasing linearly with the applied force until a limiting value. Until a limiting value. Okay? And this limiting value in that specific case was 227 in the case of the simulation. Okay. You gotta remember this behavior of the force of static friction, okay? Here you go. Maximum value, I write that down like maximum value of the force of static friction. Let's subscript, okay? Here you go. That's the maximum value of force of static friction. And then did you notice what happened in that simulation? Okay, we go all the way down to 227, right? Here you go. 50, 100. Here you go, let's go again. The force of static friction keep on increasing. And then when we reach its limit, suddenly what happens to the value of the force of static friction? Is going to be 227. Let's see. Some of the force is 0. Let's see. Okay, it's going to be right now. The maximum value of force of static friction is 227. And then when the object starts moving, the force of friction decreases in a big way. Okay? The force of friction decreases in a big way. How do we illustrate that in the graph? We illustrate like that. Here you go. Once we reach the maximum value of the force of static friction, there is this drop in the value of the force of friction. Okay, here you go. The force and the object starts to move greater than 0. At this point, you no longer have a force of static friction because the object is moving. At this point, we have the force of kinetic friction, which is usually less than the maximum value of the force of static friction. Remember, it's the maximum value, okay? It's not the force of static friction, but it's the maximum value of the force of static friction. Okay, that's why that object started to accelerate. Let's do that again. Here you go. Going back 50, right? 50, 100, 200. Here you go. We're gonna go to 228. When you get to 228, there will be a difference in force. There will be a net force difference of 0, and the object is going to, oh, watch it, yeah, and the object is going to accelerate to the right. Look at the speed here increasing. Okay, so here you go. It's slowing down, it's slowing down. Good. Okay. So things no other, we can write it down in words here. We have what, 15 more minutes to go, right? Any questions? Okay. Since no other external forces apply to the object, the force of static friction is going to be 0. as we increase the external force, the force of static friction also increases. But it increases only up to a certain point, but it increases only up to a certain point. The certain point is called the maximum value of the force of static friction. Okay. If the applied force exceeds this maximum value, then the force of static friction ceases to exist, comma, and it becomes the force. If the applied force exceeds this maximum value, no, let's do it this way. Then the net force will be greater than 0, and the object will start to accelerate like that, right? Since the object is now moving, the force of static friction becomes the force of kinetic friction, which is usually less than the maximum value of the force of static friction. Okay, gonna be like that usually. Okay, not always, but it's never greater. Okay, it's never greater than that. The force of kinetic friction is never greater than that. Usually. Sometimes under certain conditions, it can be equal. Since the object is not moving, the force of friction becomes a force of kinetic friction. At this point, if you do not do anything with your applied force, comma, the object will continue to accelerate. Okay, that's what you have to know. It's 11:50 right now. Here we go. Let's see. Take a look at the book. Okay, concept of force and mass. Newton's first law of motion we covered. Newton's second law of motion we covered. We covered the fact that the force is vectorial in nature. And we still have to talk about third law of motion, okay? There are several different types of motion, of forces, and we talked about that as well, right? Don't worry about the strong nuclear force. Don't worry about the electric force, okay? It's too much for this course. Gravitational force is enough for you right now. Here you go, the normal force that I mentioned to you. The static and kinetic frictional forces. Here you go. Let's see if they have a, here you go. How do they come about? Well, there are some irregularities. You have one interface in contact with another interface. You have some irregularities. microscopic contact points that interfere with the motion of the object. Okay. Here you go. We have this example. As I increase my force, the force of static friction also increases up to a maximum value. Okay. Up to a maximum value. Yeah, he wrote that down, superscript max. Okay. What else do I have to tell you? Okay, there's an equation for that. There's an equation for that, for the maximum value of the force of static friction. Let's talk about that. You go. It's we cannot prove that mathematically, so you have to memorize that. Okay, here you go. It's raining pretty strong here, man. If hopefully my light is not gonna go off. Okay. If my light goes off, just stay online there for a few minutes, okay? And I will get hooked up with my cell phone, okay? So here you go. Force, maximum value of force of static friction. Maximum, what's the value? It's gonna be given by by a coefficient that we call coefficient of static friction times the normal force. Okay. Don't forget that your regular force of static friction is going to be greater or equal than 0. Let's hope there is no power. The power doesn't go away here. Do you hear the thunderstorm out there? Here you go. Those are the values. No, you don't hear? Wow. Yeah, it's really strong, man. Okay, so the force of static friction has this spectrum of values between 0 and maximum value. And the maximum value is given by this equation. Is that what you have to know, that it depends on the normal force, but depends also in a parameter that we call the coefficient of static friction. Let me write that down here. Mu sub s let's see. Okay, now momentarily. So we have 2 more minutes to go. Okay, and do you have any questions? So I covered almost everything I want to know, or I wanted to cover for the force of friction. And let me see if I can. Right now I'm with my cell phone here. Okay. And let me stop recording too. We can stop recording.